You know, wind turbines. They're everywhere these days, almost part of the furniture of our landscape. But the way they're designed, the reason they have that specific shape, is a really fascinating story of physics and clever engineering. So let's get into it and break down how they really work.
You've seen them, right? Standing like quiet giants in fields or out at sea, spinning away. On the surface, it looks pretty simple, big propellers being pushed by the wind. But there's so much more going on.
Have you ever really stopped and wondered what's happening up there? How do those blades turn the invisible force of the wind into the electricity that powers our homes? Well, that's what we're going to find out.
Okay, to understand any wind turbine, you have to get your head around two key forces. It really all boils down to a battle between a simple push and a much cleverer pull. In physics, they call them drag and lift.
I mean, at the end of the day, wind is just air on the move, and anything that's moving has what's called kinetic energy. The whole job of a wind turbine is to snatch as much of that energy out of the air as it possibly can. And pretty much every turbine out there falls into one of two main camps, and it's all about which way the main shaft is pointing. You've got the super familiar horizontal axis design, and then you've got this other, less common but really interesting design, the vertical axis turbine.
So let's start with the most obvious way to catch the wind. You just let it push you. This is the whole idea behind drag. You know this feeling, right? Stick your hand out of a moving car window with your palm open. That force pushing it back, that's drag. A drag-based turbine works the exact same way. The wind slams into a blade and just shoves it around in a circle. It's simple, it's reliable, but it's got a huge drawback. And here's the problem. Right here in this diagram. Because the blade is just getting pushed, it can never ever move faster than the wind that's pushing it. Think about it. It's like trying to outrun the very thing that's shoving you forward. It's just not possible.
And that physical speed limit translates directly into a hard cap on efficiency. The absolute best a drag-based machine can ever do, theoretically, is capture about 22% of the wind's energy. Not bad, but we can do way, way better. Okay, so if pushing isn't that great, what's the alternative? This is where things get really clever. This is where turbine designers started borrowing ideas from a totally different world, the world of aviation. This is about lift. See, the blades on a modern turbine aren't just big paddles. They're basically airplane wings stood on their side. They're called airfoils, and as wind flows over that curved shape, it creates a difference in pressure, and that generates lift. It's a force that pulls the blade forward. And here's the absolute game changer. That pulling force lets the tips of the blades move much, much faster than the wind itself. Take a look at this diagram. It shows you exactly what's happening. That special airfoil shape creates a low-pressure zone that literally sucks the blade around. The blade isn't just catching the wind anymore, it's using aerodynamics to fly through it. So how much better is this? Well, this little aerodynamic trick more than doubles the potential efficiency. Because the blades are slicing through the air faster than the wind is blowing, they cover a much bigger area and grab way more energy. Now, physics says you can't capture 100%. There's a hard speed limit for wind power called the Betz limit, and it's about 59%. That is a massive jump from 22. All right, so we've got our two competing forces, the simple push of drag versus the sophisticated pull of lift. Now let's see how these principles play out in those two main turbine designs we talked about, vertical versus horizontal. Okay, so it all comes down to trade-offs. Vertical axis turbines, or VAWTs, have some really cool advantages. They can take wind from any direction, so they don't need to turn, and all the heavy stuff, the generator, the gearbox, is on the ground, which makes maintenance way easier. But they're just not as efficient. On the other side, horizontal axis turbines, or HAWTs, are incredibly efficient, and because they're so tall, they can reach the stronger, more stable winds way up high. The downside? They're complex. They need a whole system to keep them pointed at the wind, and they are enormous, making them a real headache to transport and build. And you can really see those differences in how they look. On the left, you've got some of the different vertical axis designs. They look kind of like giant egg beaters. And on the right, you have the classic shape we all recognize, the horizontal axis turbine. So in this big engineering showdown, which design actually wins when it comes to making serious amounts of power for the grid? Well, the answer couldn't be clearer. I mean, this quote really says it all. For big commercial scale power, one design has totally taken over: the three-bladed horizontal axis turbine. It turns out, when you're trying to power a country, Efficiency is king. So let's pop the hood on this winning design. All the important machinery is packed into that box at the very top, right behind the blades. It's called the nacelle. Inside there, you've got a gearbox to speed up the rotation, the generator to actually make the electricity, and a whole bunch of computers to control everything. It's a powerhouse in the sky. So, to sum it up, this design is on top for 4 main reasons. First, and most importantly, it uses that super efficient lift principle. Second, being so tall gets it up into the good wind. Third, the blades can actually twist or change their pitch to catch the perfect amount of wind. And finally, that yaw system keeps it pointed right into the wind all the time. So, the big takeaway here is this. The next time you see one of those massive 3-bladed turbines spinning on the horizon, remember that its shape is no accident. It is the highly tuned, super optimized winner of a long battle between physics and engineering. But all this leaves us with one final, very cool question. The horizontal axis turbine has been the champion for decades now, but as we get better materials, smarter computers, could a totally new design come along and take the crown? Maybe even a new take on the vertical axis idea? That's what engineers are working on right now.